300 miles off the coast of Oregon, nearly a mile beneath the surface of the Pacific Ocean, a volcano is inflating. Slowly, steadily, the seafloor above it is rising as magma pushes upward from below, building pressure inside a chamber that has erupted 3 times in the last 30 years. Scientists have been watching it in real time through one of the most advanced underwater monitoring systems ever built, and their prediction is specific: it'll erupt again before the end of 2026. That alone would be remarkable. Volcanic eruptions are among the hardest natural events on the planet to forecast, and doing it months in advance is something the field has almost never achieved. But this is not the only underwater volcano demanding attention in the Pacific right now. In May of this year, a completely unmapped volcano erupted without warning in the Bismarck Sea near Papua New Guinea. And in March, researchers in Japan confirmed that the magma reservoir beneath one of the most powerful supervolcanoes on Earth, one that produced the largest eruption of the last 10,000 years, is actively refilling 3 volcanoes, 3 different stages of the same cycle, and all of them hidden beneath the ocean. In a part of the planet we have mapped less thoroughly than the surface of Mars, the volcano is called Axial Seamount. It sits on the Juan de Fuca Ridge, a divergent plate boundary where 2 tectonic plates are pulling apart and new ocean floors being created in the gap between them. Its summit Caldera lies roughly 1,500 meters below the surface, making it completely invisible from any ship or shore. But invisible does not mean unmonitored. Axial Seamount is the most heavily instrumented underwater volcano on Earth. The regional cabled array, operated through Oregon State University's Hatfield Marine Science Center, runs more than 660 miles of fiber optic cable across the seafloor, connecting over 140 individual instruments directly to the volcano. Seismometers track every tremor. Pressure sensors measure the rise and fall of the seafloor with millimeter precision. Cameras watch hydrothermal vents in real time. Temperature probes monitor heat flow from the interior. The data streams continuously to shore, 24 hours a day, 365 days a year. This is why scientists can say what they are saying. Axial Seamount has erupted roughly 50 times in the last 800 years. In the modern era, it erupted in 1998, again in 2011, and again in 2015. After each eruption, the same cycle repeats. The caldera floor deflates as magma drains out, then gradually begins inflating again as fresh magma rises from below and refills the reservoir. Seismicity climbs, the seafloor swells, and when the inflation reaches a critical threshold, the volcano erupts. Volcanologist Bill Chadwick at Oregon State successfully forecast the 2015 eruption using this pattern. After that eruption, inflation began again. By late 2024, rates of both inflation and seismicity had picked up sharply, prompting Chadwick and his colleagues to predict an eruption before the end of 2025. It did not happen. The inflation rate was steady, but the seismicity remained lower than expected. In December 2025, Chadwick presented updated analysis at the American Geophysical Union's annual meeting. The inflation threshold needed for each successive eruption appears to increase slightly. The current ground level is now roughly 10 centimeters higher than it was before the 2015 eruption, with perhaps as much as 20 centimeters more to go before the next failure point is reached. Based on the exponential relationship between uplift and seismicity, his team now expects that threshold to be reached before the end of 2026. The researchers are candid about the uncertainty. They have acknowledged publicly that they have repeatedly pushed the forecast forward and that eventually, if they keep doing so, they will be correct simply by default. But they frame this explicitly as an experiment, an attempt to push the boundaries of long-term eruption forecasting at a volcano that is extremely active, well instrumented, and poses no direct hazard to human populations. It is, in their words, a perfect natural laboratory. When Axial Seamount erupts, it does not explode, it cracks open. The enormous pressure of 1,500 meters of ocean water above the summit suppresses the kind of explosive fragmentation that drives eruptions on land. Instead, fissures split the caldera floor and magma oozes out, spreading across the seafloor as lava flows that create new oceanic crust in real time. The 2015 eruption produced lava flows that covered roughly 150 square meters of seafloor within the caldera. Scientists observed it through the cabled instruments and were able to document the eruption sequence in unprecedented detail, from the initial inflation spike to the swarm of earthquakes that accompanied the dike. Intrusion to the deflation that followed as the reservoir drained, no tsunami was generated, no coastal communities were affected. The eruption was scientifically significant precisely because it was physically harmless. That distinction matters because it is the reason Axial Seamount has become the testing ground for volcanic eruption forecasting worldwide. If scientists can learn to reliably predict eruptions at a well-monitored, frequently erupting, low-hazard underwater volcano, those methods can eventually be adapted and applied to volcanoes that do pose catastrophic risk. Every eruption cycle at Axial is a data point. Every prediction, whether it lands or misses, teaches the field something about how magma systems behave. And if the next eruption does arrive within the 2026 forecast window, it will be one of the most precisely anticipated volcanic events in history. While Axial Seamount has been watched for decades, the next event in the Pacific arrived with no warning at all. On May 8, 2026, seismic instruments at the Rabaul Volcano Observatory in Papua New Guinea detected unusual signals, originating from the central Bismarck Sea, roughly 130 kilometers southeast of Manus Island. Within days, satellites confirmed what the seismometers had flagged. A submarine eruption was underway. Steam and ash plumes were rising from the ocean surface. The surrounding water had turned an opaque green, and there was a problem. When scientists looked for the source on existing maps, there was nothing there. No charted volcano, no mapped vent, no bathymetric record of any volcanic structure in the immediate area. The volcano that was erupting had not been included in any database. Oceanographers pointed out afterward what they have been saying for years. We have mapped the surfaces of the Moon and Mars in greater detail than much of the deep ocean floor. The Bismarck Sea is a particularly stark example, a geologically complex basin riddled with faults, rifts, spreading zones, and subduction boundaries, almost none of which have been surveyed at high resolution. The eruption site was eventually linked to a feature called the Titan Ridge, which had only been included in a regional geological map published in 2024 by researchers at Geomar Helmholtz Center for Ocean Research in Germany. Before the eruption, the summit of the Titan Ridge volcano sat more than 400 meters below the surface. By mid-May, satellites were tracking emissions from two separate vent areas roughly 2.5 kilometers apart. Ash and pumice were being ejected in volumes large enough to be visible from space. By early June, massive floating pumice rafts had drifted westward and begun washing ashore on the coastlines of Manus Island, blocking harbors and inundating beaches. Local residents described it as a disaster. NASA's Earth Observatory, using Landsat 9 and other orbital platforms, tracked the eruption's evolution in detail. Scientists noted that if the eruption continued long enough and built the volcanic edifice close enough to the surface, a new island could potentially emerge, the way Hunga Tonga Hunga Humapai temporarily created new land before its catastrophic explosion in 2022. As of late July, the eruption at Titan Ridge was still ongoing. What makes underwater volcanoes dangerous is not the lava, it is the water. The 2022 eruption of Hunga Tonga Hunga Humapai in the South Pacific demonstrated this in the most dramatic terms imaginable. On January 15th of that year, the submarine volcano exploded with an estimated force of roughly 61 megatons of TNT equivalent. The eruption column punched through the stratosphere and reached a record height of 58 kilometers, higher than any volcanic plume ever recorded by modern instruments. The blast was heard in Alaska. Atmospheric shock waves circled the planet at least 5 times over several days. Detected by weather stations on every continent, tsunami waves reached coastlines throughout the Pacific and beyond, traveling at speeds far faster than conventional tsunamis because they were partly driven by the atmospheric pressure wave itself rather than only by ocean displacement. Maximum wave heights on the coast of nearby Tongatapu reached 15 meters. Roughly 80% of Tonga's population was affected. Entire villages were destroyed. Communications were severed for days after the eruption damaged undersea telecommunications cables. Yet remarkably, only 4 people died in Tonga itself, a figure attributed largely to effective tsunami preparedness and the population's familiarity with volcanic hazards. 2 additional deaths were reported in Peru, thousands of kilometers away, where the tsunami arrived faster than expected because of the atmospheric coupling effect. The eruption injected an unprecedented volume of water vapor into the stratosphere, between 50 and 150 million metric tons. A study published in the Journal of Climate in July 2026 found that This injection is still affecting global weather patterns years later, contributing to an unusually large ozone hole and wetter than expected conditions in parts of the southern hemisphere. The effects could persist through the rest of the decade. Hunga, Tonga was classified as the largest underwater explosion ever recorded by modern scientific instruments. It was also a reminder that the ocean floor hosts volcanic systems capable of producing globally significant events with almost no advance warning. In March 2026, a team of researchers at Kobe University in Japan published a study in Communications, Earth and Environment that confirmed something scientists had suspected but had never directly demonstrated. The magma reservoir beneath the Kikai caldera, and a 19-kilometer wide depression lying mostly underwater south of Japan's Kyushu Island, is actively refilling with fresh magma from below. The Kikai caldera is not an ordinary volcano. Approximately 7,300 years ago, it produced the largest volcanic eruption of the Holocene, the geological epoch that covers all of recorded human history. That eruption, classified as VEI 7, ejected between 133 and 183 cubic kilometers of material, pyroclastic flows, superheated clouds of gas and rock moving at hundreds of kilometers per hour, traveled more than 100 kilometers across the open ocean surface. Volcanic ash from the eruption has been found in sediment layers as far away as Hokkaido, over 1,000 kilometers to the north. The entire southern portion of Kyushu was devastated. The civilization living there, the Jomon people, left no written record of the event. The eruption was so massive that the roof of the magma chamber collapsed, forming the caldera that exists today beneath the sea. What the 2026 study found is that the reservoir beneath that caldera is not dormant, using airgun arrays to generate controlled seismic pulses and ocean bottom seismometers to track how those waves travel through the crust. The team detected a large low-velocity anomaly directly beneath the caldera at depths of just 2.5 to 6 kilometers. Low-velocity anomalies in seismic data indicate the presence of partially molten rock. The researchers confirmed that this is the same magma reservoir that fed the eruption 7,300 years ago. But the magma now filling it is chemically distinct from the material that erupted in the Holocene event. It is new magma being injected from deeper in the mantle, not leftover material, slowly cooling from the previous eruption. The lead researchers stated plainly that understanding how such large quantities of magma accumulate is essential to the deep. Understanding how giant caldera eruptions occur, the reinjection model they developed is consistent with observations at other supervolcano systems, including Yellowstone in the United States and Toba in Indonesia. None of this means an eruption at Kikai is imminent. Supervolcano systems operate on timescales of thousands to tens of thousands of years, but the discovery that the reservoir is actively rebuilding rather than passively cooling changes how scientists model the long-term behavior of these systems, and it raises the question of how many other submarine calderas around the Pacific are doing the same thing without anyone watching. This is the part of the story that rarely gets the attention it deserves. We do not know where most of the world's underwater volcanoes are. Current estimates suggest there are more than 1 million submarine volcanic features on the ocean. 4. Fewer than 100,000 have been mapped at any resolution. Fewer still have been surveyed with the kind of detail needed to assess their eruptive potential or monitor their current activity. The Titan Ridge eruption in the Bismarck Sea proved the point in the starkest possible terms. A volcano that was not in any database erupted without warning in one of the most tectonically active ocean basins on the planet. If it had been located closer to a populated coastline, the consequences could have been severe. The Bismarck Sea is not unique in its poor mapping coverage. Large sections of the Pacific, Indian, and Southern Oceans remain virtually unsurveyed at the seafloor level. The technology to map them exists: multi-beam sonar, satellite altimetry, autonomous underwater vehicles, and cabled observatory systems are all proven tools. But deploying them at scale across millions of square kilometers of deep ocean requires sustained investment that has never materialized. The Seabed 2030 project, a global initiative launched in 2017, aims to produce a complete high-resolution map of the world's ocean floor by the end of this decade. As of early 2026, roughly 28% of the ocean floor had been mapped at the target resolution. That is a significant improvement from the 6% that existed when the project began, but it means more than 70% of the seafloor remains effectively unknown. Every unmapped volcanic ridge, every unsurveyed caldera, every uncharted seamount, and that 70% is a potential source of seismic activity, eruption, or tsunami generation that we currently have no way to anticipate. The Pacific Ocean is ringed by the most concentrated belt of volcanic and seismic activity on Earth, the Ring of Fire, a roughly 40,000-kilometer horseshoe-shaped zone stretching from New Zealand through Southeast Asia, Japan, the Aleutian Islands, and down the western coasts of North and South America, contains approximately 75% of the world's active and dormant volcanoes and accounts for roughly 90% of the planet's earthquakes. Most of the attention these systems receive focuses on the volcanoes that sit above the waterline: Mount Fuji, Mount Rainier, Mount Pinatubo, Krakatoa, but the majority of volcanic activity on Earth occurs underwater, along the mid-ocean ridges and subduction zones that crisscross the ocean floor. The Juan de Fuca Ridge, where Axial Seamount sits, is one small segment of the global mid-ocean ridge system, the longest mountain range on the planet, stretching more than 65,000 kilometers across every major ocean basin. Eruptions along the system are continuous. New seafloor is being created constantly. Most of it happens in places so remote and so deep that no instrument records it. What makes the current moment unusual is not that underwater volcanoes are erupting. They are always erupting somewhere. What makes it unusual is that we are watching 3 different systems in 3 different stages of the volcanic cycle at the same time. Axial Seamount is approaching eruption. Titan Ridge is actively erupting. Kikai Caldera is recharging for a future eruption that may be thousands of years away or may never come at the same scale again. Together, they illustrate a complete arc of volcanic behavior. From buildup to eruption, to recovery, to rebuilding, playing out simultaneously across the floor of a single ocean. The word shocking in the context of these volcanoes does not mean what most people assume. The shocking part is not that any of them will erupt. The shocking part is the range of timescales involved and how little separates the ones we can predict from the ones we cannot. Axial Seamount may erupt within months. Scientists can say that because it has been instrumented for decades, it erupts frequently, and its behavior follows a measurable pattern. Titan Ridge erupted without warning because nobody knew it was there. No instruments, no baseline data, no pattern to recognize. Kikai Caldera is rebuilding on a timescale of millennia, but the magma reservoir feeding it is sitting just 2.5 kilometers below the seafloor, shallow enough that any significant change in activity would be detectable if the instruments were in place. The gap between prediction and surprise, in every case, comes down to the same variable: whether anyone was watching. Axial is the proof of concept. It demonstrates that long-term eruption forecasting is possible when the monitoring infrastructure exists and the data is continuous. Titan Ridge is the warning. It demonstrates what happens when it does not. And Kikai is the longer question, the one that asks whether humanity is prepared to monitor systems that operate on timescales far longer than any government's budget cycle, any research grant, or any human career. Right now, beneath the Pacific Ocean, magma is rising. At Axial Seamount, pressure sensors are recording the slow, steady inflation of a caldera floor that is approaching a threshold scientists have identified, measured, and published. At Titan Ridge, an eruption that began on an unmapped volcano is still producing pumice and ash visible from space. And beneath the water south of Japan, a reservoir that once fed the most powerful eruption of the last 10,000 years is quietly filling with fresh, molten rock from deep inside the earth. None of these systems are visible from the surface. None of them make noise that carries through the air. If every instrument monitoring them went offline tomorrow, the volcanoes would continue doing exactly what they are doing, inflating, erupting, recharging, with no one the wiser until the consequences reach the surface. We mapped the far side of the moon in 1959. We mapped the surface of Mars in high resolution by the early 2000s. As of 2026, we have mapped less than 30% of our own ocean floor. The volcanoes are not hiding. We just have not looked.